Hi, so in this video, we'll be solving an air conditioning problem that is integrated with a refrigeration system. Okay, so let's proceed. The first thing we always do is we make sure that we draw a diagram. Okay, since we'll be incorporating a refrigeration system, let's make use of the refrigeration system for cooling the air. So for our first part, we draw the evaporator. After the evaporator, you have your compressor. It's very little. After your compressor, your refrigerant will go through the condenser. Okay. After the condenser, it will then go through the expansion valve. Alright. So, how will we cool the air? The evaporator will act as our heat exchanger. When you have your coils wrapped around the heat exchanger. Okay. So we have outside air going in and air going out. Okay, what are the other givens? So air going in, we have 6,000 cubic meters per minute, and then we have a total pressure of 98 kilopascals, 85% relative humidity, and dry bulb temperature of 30 degrees Celsius. Okay, so air going out, we have a dry bulb temperature of 15 degrees Celsius and a relative humidity of 70% RH. Okay, what else do we have? So notice that we are given a refrigerant which is R134A or Freon, and evaporating temperature is at lower limit temperature of 60 degrees Celsius and condensing temperature of 48 degrees Celsius. Okay, right. So what's the first step that we gotta do? Notice that we are required to solve a lot. Sorry. There's a lot of requireds in the problem, right? We must find the dew point temperature here at the outside air going in, kilograms of water that is condensed in a day. That means as your air passes through the coil, there will be droplets of water that will be condensing at this part. Okay, tons of refrigeration is just how much energy was used to cool your air as it cools from 30 degrees Celsius to 15 degrees Celsius given their relative humidity. Okay, so the amount of refrigerant, the amount of R134A that you must use to cool your air, right? And the COP is just the tons of refrigeration over the actual work that is going in. That's just the ratio of the COP. And the amount of water coolant circulated in the condenser if its temperature change is 10 degrees in kilograms per second, right? So the first thing that we must do, since we need most of the properties, we'll just write the equation that we need to use, okay? By the way, in this video, we're not using a steam table, right? But we'll be using the table for properties of refrigerant R134A later on. Okay? So, what's the first equation that we will be introducing? Okay? So first, we'll introduce the saturated pressure equation coming from Paris Chemical Engineering Handbook. So our first equation is to solve the saturated pressure, limits of 0 degrees Celsius to 80 degrees Celsius. Unit will be in pascals, and the equation is here. Okay, so let us say that this is our equation 1. Okay, so equation 1. What else do we need? We need the relative humidity equation, where simply it is a ratio of your vapor pressure over your saturated pressure. Okay, let's name this our equation 2, right? Okay, what else? We need the humidity ratio, which will be assigning a nomenclature of W. It's 0.622 PV PT minus PV. Okay, this is our equation 3. Now on my other videos, we'll be deriving the equations and we'll be discussing how they are derived, right? Especially with these numbers. They came from the molecular weight of water, ratio of the molecular weight of water to molecular weight of air. Okay, what else do we need? We need the ideal gas equation, but in this case, since the ideal gas equation is PV equals mRT, we will not use the universal R, which is 8.314. We'll use the gas constant for air, which is 0.28708 kilojoules per kilograms Kelvin. Alright. So if we want the density, we can see, if we rearrange the equation, put the V under, we will have M over V, right? So it works like this. You put the V here, and then you put the RT under, right? It's kind of like this, and then you'll be arriving at this one, okay? So M over V equals P over RT. But since we want the dry air, remember that the total pressure is wet. The total pressure is wet here, as long as you can see values of relative humidity, right? That means it contains vapor, droplets of water. The air contains droplets of water, okay? So for it to be dry, you want the total pressure minus the vapor pressure, okay? Or T. Okay. So this will be our equation. Let's convert this to red. Okay. And this will be our equation. Sorry. This is equal to your density, which is dry air. Equation 4. Right? Okay. So how about enthalpy? Again, we have enthalpy, which is H, limits of 0 to 60 degrees Celsius, right? It's in kilojoules per kilogram. It's 1.007 dry bulb temperature. Remember that the reference is from dry bulb temperature, always subtracted to the to 0 as the reference, minus 0.026. This is your correction factor, plus humidity ratio 2501 plus 1.84 times temperature of the dry bulb, again from dry bulb temperature to 0, so you just simply multiply that, okay? So this will be our equation 5. Equation 5. Right. So what else do we need? Okay. So if we're talking about the kilogram of water that will be condensed in a day, note that the amount of air going in your cooling coil contains a relative amount of water vapor. Now as you cool that, the amount of water vapor it can hold is lesser than the amount of vapor you can hold at 30 degrees Celsius. So as you cool the air, droplets of water will start to liquefy or condense, okay? Because it really cannot contain that amount of the relatively large amount of water vapor compared to 30 degrees Celsius. So what is the equation we'll be using for uh, amount of H2O condensed? It's mass of air going in times the difference between this humidity ratio of the air going in minus the humidity ratio of air going out. Okay, so this will be our equation 6. What else? Tons of refrigeration is simply the amount of energy that you are required to cool the air. Okay, since we're talking about energy, we'll be including enthalpies in the system. So your tons of refrigeration is simply your mass of air going in times the difference in mass of air going in minus the enthalpy of air going in and then enthalpy of air going out. Okay, so let this be our equation 7. So what else? Okay, COP again, recalling our refrigeration systems. COP is simply the ratio the amount of energy you put or the amount of energy required to cool your evaporator over the amount of actual energy that is required to run your compressor. Okay, so it's PR over work compressor actual. Okay, this is our equation 8. What else? Okay, D and F are kind of the same. When it states on the problem that you're asking for the amount of refrigerant, amount of water, given the temperature change, in this case you will be having enthalpies, no? So simply it's gonna be Q in equals Q out, wherein Q may be MCP delta T, or Q may be M delta H with respect to H in and H out. Okay, so this will be our equation 9. Okay, so let's first try to solve A, B, and C. Okay, so we'll put it here. Right, okay. So what's the first thing that we have to find? Since we're required to have a lot of things here to solve the problem efficiently, let's just get all the properties that we can, especially properties going in, and let's just look at the properties that we can find going out. Okay, Okay. So at air in, we have we can find the vapor pressure using our relative humidity equation, but we don't have the saturated pressure. So at air in, at 30 degrees Celsius, P sat at 30 degrees Celsius via equation 1. P sat is around, so let's just put it here in our calculator. Okay. So this is our equation. We input the equation on our calculator, just press calc and put whatever temperature it is, assuming it's between 0 and 80 degrees Celsius. At 30 degrees Celsius, you have saturated pressure of 4.248 kilopascals. Okay. How about air going out? So at 15 degrees Celsius via equation 1, P sat is 15 degrees equals 1.7053 kilopascals. Okay. What else? Via equation 2, at 0.85 RH, and what else? PSAT equals 4.248 kilopascals. Vapor pressure is equal to, so we'll be using our relative humidity equation. Okay, so 0.85 equals, let X be our vapor pressure, 4.248. Vapor pressure is 3.6108 kilopascals. Okay. So via equation 2, at 0.70 or H and PSAT is 1.7053 kilopascals. Vapor pressure is 1.19371 kilopascals. Okay. Right. So what else do we need? We need the humidity ratio. Okay. So via equation 3, right? Via equation 3, what's our equation 3? It's 0.622 PV. Okay. We have our PV already, the vapor pressure, and PT is, okay, at PV equals what? 3.6108 kPa. PT is 98 kPa. W in is what? 0.023794 kilograms of vapor over kilograms of dry air. Again, on our separate video, we have discussed there that the concept of the total pressure, if you have a vapor pressure existing, notice that your air will be wet, and through Dalton's law of pressure, it is the corresponding amount of moles or mass of your air is equal to the ratio as well of your vapor pressure to your total pressure. Okay, moving on, air going out via equation 3 at PV equals 1.19371 kilopascals. Total pressure is still 98 kilopascals. Humidity ratio going out is around 0.00767 kilograms of vapor over kilograms of dry air. Okay, what else? So via equation 5, I'll not put the given that we can just use the equation 5 with all the conditions of air going in and air going out. Okay, via equation 5, H equals, as you can see, okay, H equals 1.07. Dry bulb temperature is 30 degrees Celsius minus 0.027 plus humidity ratio is 0.023794 times 2501 plus 0.84 times 30 degrees Celsius. Right? So we'll see that the enthalpy is around 91.005 kilojoules per kilogram. Okay, same here via equation 5. H is, so instead of using 30 degrees Celsius, okay, instead of using 30 degrees Celsius, we'll use 15 degrees. And instead of using the in condition of your humidity ratio, use your 0.00767. Okay, enthalpy going out is what? 34.472 kilojoules per kilogram. What else? Via equation 4. Via equation 4, the density of air is what? So again, what is our equation 4? It's PT minus PV over RT. PT minus PV is what? 98 minus vapor pressure is 3.6108 over 0.28708, 30 degrees plus 273. And there's really no difference, or there's little difference if you'll use 0.15, which is the absolute temperature in chemistry. but for transparency purposes, I guess in other courses and programs, mechanical engineering aside, civil engineering and anywhere else, it's 273. They're using 273 as their absolute temperature. Okay, so let's just use 273. But the most accurate is 273.15. Okay, well, we can use 0.15. So 1.0846 kilograms of dry air over cubic meters. Okay, so that's all we need. Now let's proceed in solving letter A. Okay. So, what's the first thing that we have to look out for? Let's try to find the mass of air going in. So the mass of air going in is, since we have the volumetric flow rate, we know that we really just have to convert this one. 6,000 cubic meters. If this is per minute, I want to use per second, since later on we'll be using kilowatts or kilojoules per second. Let's just say this is 60 seconds. Okay. Times, what's your density? Density is 1.0846 kilograms of dry air over cubic meter. So this will be your mass flow rate of air going in. Mass flow rate of air going in is 108.46 kilograms per second. Okay. Right. So what is A asking us for? They're asking to find the dew point temperature in degrees Celsius of the outside air. Again, dew point temperature is the corresponding temperature at its vapor pressure, wherein vapor pressure of the outside air is 3.6108 kilopascals. So via equation 1, just plug in equation 1. What's your equation 1? It's E, 73.649. That's 7258.2. Okay, so note that the dew point temperature is always lesser than your dry bulb temperature. So via increments of 5, let's try 25. At 25 degrees Celsius, it's around 3.17 kilopascals. So it does not fit the criteria. Let's try 26. 3.364 still doesn't fit our 3.6108. Let's try 27. 3.568. Quite close. So let's try 27.1. It's not Still there, 27.2. Okay, it's almost there, right? So 3.6108 is 3.6109. I guess it really won't matter that much. So we know that the dew point temperature, using equation 1, let's just, it's very simple. Via trial and error, dew point temperature is around 27.2 degrees Celsius, okay? Okay, 27.2. What else do we need? The letter B. Amount of water that is condensed in 1 day. Okay? So via equation 6, mass of air going in is 108.46. This is kilograms of dry air per second. You want this per day. 3600 seconds. We have 1 hour times 24 hours in a day. Also, humidity ratio in is 0.023794 minus, what is out? 0.00767 kilogram vapor and kilogram dry air. Okay? We'll just cancel the units. Second, cancel. Hours, kilograms of dry air. So you are left with, let's just solve the problem first. Two, 3, 794. So the amount of water condensed is around 151,097.1 kilograms of vapor per day, or kilograms of water condensed per day. Okay. Okay, what else? Okay. Let's try letter C. Tons of refrigeration required. Okay. Let's try letter C. Tons of refrigeration, again, it's we're talking about energy. We'll be using enthalpy. Okay. So tons of refrigeration, again via equation 7. Mass of air going in is what? 108.46 kilograms per second. Enthalpy in is what? 91.005 minus 34.472 kilojoules per kilograms. Now we want this to be in tons of refrigeration. So know that every kilojoules per second, that is equivalent to kilowatts, and every 3.517 kilowatts is 1 tons of refrigeration. Okay? Okay. So this is 108.46, 3.517 times 5 minus 34.472. Okay. So the tons of refrigeration required is around 1743.41 tons of refrigeration. Okay. Okay. So what else do we need? D, E, and F. For us to solve D, E, and F, we have to find their corresponding enthalpies, okay? So, say this is our diagram again, okay? Let's name this our point 1, point 2, point 3, and point 4, okay? So, since this is a compressor and there aren't any given specific ratios, we can assume that the compressor is isentropic. What does that mean if it is isentropic? It means that the entropy of the refrigerant going in at 1 is equal to the refrigerant is equal to the entropy of the refrigerant going out. Okay? So entropy going in is equal to entropy going out. Okay? What else? What else do we need? After leaving the evaporator, the unit will be in saturated vapor, or in any case, it's your G. Okay? At 2, this will simply be your superheated refrigerant, okay? This is superheated. Okay? So, leaving the condenser at point 3, if you recall your refrigeration system, this will be saturated liquid, or your F. Okay? Right. So, let's remove it here first. Okay. Okay, for our refrigerant 134A, okay. So for our refrigerant 134A, let's try to copy the table. Let's put it here. Okay. So, what is H1? What is H1? So, let us put H1 here. H1 equals the saturated vapor, or G. So, at 6 degrees Celsius, where is that? Enthalpy is here. So, it's 253.91, alright? Saturated vapor, or your Hg. So, H1 is what? 253.91 kilojoules per kilogram. Since they are isentropic, let's also look for the S1. S1 is what? Saturated vapor as well. So let's look for the value. The value is 0.92828. Okay. Kilojoules per kilogram Kelvin. Okay. For our H2, since again we can say that the entropy going in is the same as the entropy going out. We can say that S2 is 0.92828 kilojoules per kilogram Kelvin, right? We don't have the data for the 48 degrees Celsius, but we can use it. For the 48 degrees Celsius, okay, it's simply right here. Let's put it here. Let's put it here. Okay, let's just match that. Okay. Okay. So, around 48 degrees Celsius, we really can't find the superheated value. Or we can though interpolate it, but another easy way to do it is by using the quality method. Okay, so we know that H or S is equal to the SF plus SFG times your quality X. This is also equal to your SG, quality X plus 1 minus X, and SF. Okay, same principle applies in enthalpy. HF plus HFG X is equal to your HG X plus 1 minus X HF. Okay, so at point 1 we know that the value point 2, we'll start at point 2. The value is still 0.92828. S1 equals S2 equals 0.2828. Now via the second condition, let's use this one to find the quality. 0.92828 equals, what's the SF? SF is 0.43242. So we want to find quality X at 2. So we'll be using the second conditions. Okay, degrees Celsius. 242 plus 47993. The quality of the refrigerant here will be above 1. Okay, so you have 1.03319 as your quality. Okay, so using this quality, H2 is equal to what? We'll be using 120.39 and 154.14. H2 is 279.646, I guess, kilojoules per kilograms. Okay, so we now have our value. H2 is 279.646 kilojoules per kilogram. H3 is your saturated liquid value at 48 degrees Celsius, since it's coming out at 48 degrees Celsius. Okay, at 48 degrees Celsius it came out as saturated liquid. So 48 degrees Celsius, saturated liquid. Okay, it's 120.39. Okay, kilojoules per kilogram. And notice that if the process underwent an expansion valve, it is isenthalpic, meaning you have a constant enthalpy, meaning your H4 will also be your H3. It's gonna be 120.39 kilojoules per kilogram as well. Remember, when it passes through an expansion valve, you will be having a same value for your enthalpy. Okay, so what else? Going back, what do we need? Amount of refrigerant to be circulated in the system. Okay, so let's use the tons of refrigeration here. So the amount of energy here in the evaporator is the same. Okay, that means you are required to have at least 1743.41 tons of refrigeration to cool your system. Okay, well, in that case, let's use equation 9. Okay, so letter D via equation 9. And the tons of refrigeration is always happening at the evaporator. Okay, so we have Q in equals Q out, wherein your Q in is what? Q in is 1743.41 tons of refrigeration. You have to convert it back to kilowatts. It's 1 tons of refrigeration is 3.517 kilojoules per second, or kilowatts. It's gonna be equal to M R134A times their enthalpy. Okay, remember here at equation 9, enthalpy going in and going out. Okay, it's a difference in enthalpy limits to the one going in and going out. Okay, so it's gonna be between 253.91 minus 120.39 kilojoules per kilogram. Now notice that the unit will be in what? The unit will be in what? Kilograms per second. Okay, so mass of R134A is what? So the mass of R134A will be around 45.922 kilograms per second. Okay? Right. So, let's proceed now to letter E. Okay? What is asked at letter E? COP of the refrigerating system. COP again via equation 8. Via well, there are two ways to solve for the COP. Okay? Again, COP is simply TR over the work of the compressor, actual work of the compressor. Okay? So you can simply just use this value, but you have to also find the work in kilowatts. Okay, but nonetheless they're gonna be the same. Let's try both approach. Okay, it's gonna be equal to it's gonna be equal to 1743.41 tons of refrigeration. And remember that it must be dimensionless, so the units must be consistent. Okay, so every 1 tons of refrigeration there is 3.517 kilowatts. Work of the compressor, it's gonna be, what is the mass of the refrigerant? It's gonna be 45. Right, so 279,646 minus 253.91 kilojoules per kilogram. Okay, so remember that the amount of refrigerant going in the system, if this is 45.922 kilograms per second of refrigerant, this would also be 45.922. It's the same here, assuming no losses. Okay, so what's the answer? Answer is 5.188. It's simply their ratio. Okay, now if we use the other approach, okay, it's still gonna be the same. Okay, so again, the amount of energy that you have here is between these enthalpies 1 and 4 at the evaporator. However, on the amount of energy about the compressor, it's going to be between these values, H2 and H1. Okay, it's between these 2 and 1. So let's use the values. Again, COP 253.91 minus 120.39, still in kilojoules per kilogram. It's gonna be 279.646 minus 253.91 kilojoules per kilogram. both the units will cancel out. Value is still the same, 5.188 for the COP of your refrigeration system, okay? So let's try letter F. Okay. Letter F. Amount of water coolant circulated in the condenser if its temperature change is 10 degrees in kilograms per second. So about the condenser, again, the energy required, or the energy that was rejected by the condenser, is between enthalpies of H2 and H3. Okay? Since you have your mass flow rate, you also use the mass flow rate to acquire the amount of energy that was released by the condenser. Okay? Still, it's gonna be via equation 9. Via equation 9, what's with the equation 9? We're using M delta H, meaning the amount of energy that was rejected, and we want to find the amount of water that will be used if about the condenser there is, say, a coil here that you want to cool the condenser with water. Okay. So let's try to put that here. So equals the Q of water absorbed. So let's say this is your condenser. Say this is your condenser, and this is, say you have water here. So what is this? This is your, about the condenser, this is your R134A. And this is your water, right? They're using water. It's really not mentioned in the system, but it kind of looks like this. There is a water that is used to cool your condenser, okay? So, temperature change is 10 degrees Celsius, meaning the DT is already at 10 degrees Celsius, meaning it's gonna be your T out minus T in of water. Okay, so how will we find the Q rejected? Q rejected is simply mass of the refrigerant. It's 45.922 kilograms per second. And again, between temperatures, between enthalpies of H2 and H3. Okay? So H2 is what? 279.646 minus 120.39 kilojoules per kilogram. Okay, so you have units of kilojoules per second. Okay, this is equal to what? This is your this is the Q rejected at condenser. Okay, now how about the water? it's gonna be MCP delta T. Okay, it's gonna be MCP delta T here. Okay, so mass of water, CP is 4.187. Mass of water is in what? Kilograms per second. 4.187 kilojoules per kilogram Kelvin. And remember that it's a temperature change, so it really doesn't matter if it's gonna be the same. 10 degrees Celsius will be the same as 10 degrees Kelvin, since it's a temperature change, right? It's like, say for example, you have T1 equals 30 degrees Celsius and T2 equals 40 degrees Celsius. If you convert this to absolute temperature, it's gonna be 303, and this is gonna be 313. Their temperature difference though, it's still gonna be 10. Okay, it's still gonna be 10. So again, this is your heat absorbed by water. That's why it had a temperature raise of 10 degrees Celsius. So if you solve mass of water in kilograms per second will be what? It's around 174.67 kilograms per second. Okay, right? So did we solve all the problems? I guess we did. You can just replay the video if there's a confusion. Like and subscribe. Thank you.